if we apply a disturbing force on a system for perturbing the system, then the actual response of the system can be denoted by Ct, which has two components. Just a moment. Two component. This is the output response of the system, which is basically the linear combination of the two
ম্যাম
components. One
আপনি
is,
কি স্ক্রিন শেয়ার করেননি মনে হয়?
oh sorry, screen share করিনি আমি, sorry.
Ma'am, 47 present. Hello, ma'am, 47 present.
ঠিক আছে।
Ma'am, roll 11 present.
Now can you see the material?
Yes, ma'am.
Okay. So the combined response of the system because of two forces. One is the disturbing forces which we have applied, and after that we have removed after a while, and the response of the system because of the impressed input signal. So C02 is the response of the system because of the impressed force, and CDT is the response of the system because of the disturbing force, right? So in the last class, we discussed that the stability of the system can be judged by answering this question, that is, what will happen to CDT, this component of the response, as time t tends to infinity, right? So we'll try to find out a suitable answer for this, and accordingly, we'll try to define stability of a system. Okay. Now, there could be three cases. The first case is as t time tends to infinity, as time t increases, this
Excuse me, ma'am. Hello.
yes,
Hello,
yes,
ma'am. I joined a little late because of network issues. Could you please mark my attendance?
not now.
Okay, ma'am.
Let me finish the class.
Okay, ma'am.
So t tends to infinity, this component will tend to zero. So this part will decay down, and so what will happen as time t increases, the response of the system will be same as the response when no disturbing force was applied, right? So that is a desirable situation. So the first case is this component will tend to zero, and eventually Ct will be equal to C0t. So initial response is same as the final response after the withdrawal of the disturbing force. Now, the second case could be like this, that as t tends to infinity, this component of the response will tend towards infinity. That means that particular component will go on increasing farther and farther as time t increases, right? So, or we can have sustained oscillation at the output because of the disturbing force. We can have sustained oscillation at the output with infinite amplitude. The amplitude is infinite, right? or you can have any combination of this two. So whatever be the case, under this particular situation, we see that the this particular component will not die down, rather it will go on increasing further and further, and hence the actual output of the system will go on increasing further and further as time t increases. And the third case could be like this, that as time t increases, this component will become constant, some constant k, or undamped oscillation with some constant amplitude, oscillation with finite amplitude. in in this particular case, the amplitude is not infinite, so oscillation with finite amplitude, or any combination of these two, that means k plus t, right? So
Ma'am, can you repeat this again, please?
which
Uh,
one?
the above which you have studied just now. That limit,
The
yes,
third
that.
case, the third case.
Ma'am, both the second and third case, please repeat.
So what's happening in this case, you see, this component as t tends to infinity, the this component of the response is becoming infinite, or the output of the system will observe sustained oscillation with infinite amplitude. Now sustained oscillation with infinite amplitude is not possible in reality. So instead what we'll get, we'll observe undamped oscillation. Sustained oscillation means undamped oscillation with very high amplitude, right? Or at the output, or at the output response will go on increasing farther and farther. Will go on increasing towards infinity, farther and farther as it tends to infinity, right? Or any combination of these two. And the third case is the output response, because of the disturbing force, will be a constant or finite magnitude, like a steady DC one, or will observe sustained oscillation at the output of the system with finite amplitude, right? Or any combination of this. That means a DC, and on that, yes, an undamped oscillation will be superposed. Now, have you understand? Have you
Yes, ma'am.
understood?
Yes, ma'am.
Now, so considering the above cases, now we can classify, or we can define the stability of the system, that if the response of the system to a bounded disturbing force vanishes, the response vanishes ultimately as t tends to infinity, that means the first case, then the system will be stable, because the system will now exhibit the unperturbed oscillation, which is unperturbed response, that is C0t. That means the system has regained its initial condition of motion. Is it clear?
Yes, ma'am.
Hello, ma'am. I was having internet issues, so I wasn't able to join earlier. I joined around 6:45, so could you please record my attendance?
Actually, I did expect a little bit common sense from your side. So when I'm taking the class, why are you interrupting me for your attendance? Let me finish the class,
I'm sorry, ma'am.
then you
I'm
raise
really
the
sorry.
issue.
Oh, okay, ma'am. No, actually, my connection is a bit poor today, so I wasn't able to follow the class properly.
So if the system exhibits the dynamic behavior as described in case 1, the system will be classified as a stable system. Now, case 2, if the response of the system to a bounded disturbing force ultimately becomes an infinite amplitude or unbounded. Infinite amplitude means unbounded, or an oscillation of infinite amplitude that is also unbounded because the magnitude of the oscillation is very, very high, right? So, though the system was parted by a bounded disturbing force, the system is exhibiting unbounded response at the output. So we cannot work with that particular system, and hence the system will be unstable, will said to be unstable. And the third case is a very interesting one. The third case where the at the output will get a finite amplitude or finite amplitude undamped oscillation. So that particular case cannot be classified either as a stable case or an unstable case. That means system exhibiting such a kind of behavior cannot be said to be a perfectly stable one or cannot be said to be an unstable one. Instead, we use a term for describing such systems, and the system is limitedly stable. So, why the system cannot be classified as a stable one or an unstable one? Because at the output of the system, at the output of the system, this amount of deviation, if the system engineer, if the control system engineer, or if you can allow this amount of deviation at the output, then yes, you can work with that particular system. Or at the output, if you can allow this kind of small undamped oscillation, then you can work with that particular system. So then the system will be considered to be a stable one. But if the value or the magnitude of k is such that that much of deviation at the output cannot be tolerated, or if the amplitude of the sustained oscillation, undamped oscillation O, is quite high and that cannot be allowed at the output of the system, then obviously will not be able to work with that particular system, and hence the system will be considered to be an unstable one. So in general, the system exhibiting this kind of response or responses is called limitedly stable one. Have you understood?
Okay, repeat it once again.
Which part?
That damped part, that time variance, the damped part.
Time variant damp part? I never use the term time variant.
I think that a function of time, the amplitude, that one, k and theta t.
This is not theta t, this is OT. This
Oh,
is
sorry,
not
sorry, sorry.
theta. OT is basically, with the help of this notation, we are representing that at the output we are getting undamped oscillation with finite amplitude. That means at the output we are getting a signal like a sinusoid with a finite amplitude, right? Or in the first case, at the output of the system, we are getting a DC kind of a signal that is constant. Okay.
Yes, ma'am.
Now, this particular system exhibiting this kind of responses cannot be termed as a stable one or an unstable one. Why? Because if the value of k is pretty small and if we can allow this much of deviation at the output of the system, okay, then we can work with that particular system. So the system will be considered to be a stable one. Similarly, at the output of the system, if we find a very small amplitude sustained oscillation which can be permitted, which can be allowed, then we can work with that particular system, and then the system will be considered to as a stable one. But if the amplitude is such, if the value of k, magnitude of k is pretty high, or if this amplitude of oscillation O, this is pretty high, And if we cannot allow this amount of deviation at the output or sustained oscillation at the output, then we are not in a position to work with the with that particular system, and hence the system will be considered to be an unstable one. Now, is it clear?
Okay, ma'am. Okay, ma'am.
So that's why, in general, this kind of systems are described as limitedly stable one. Now, one thing that the second case for an unstable system that I must mention, for an unstable system, we saw that at the output, the amplitude, the output response is increasing towards infinity, or we are getting a sustained oscillation with infinite amplitude. As I said, in reality, will not the output will not tend towards infinity, or will not get sustained oscillation having infinite amplitude. What may happen, the output amplitude, the amplitude of the response, magnitude of the response will be very, very large, which cannot be tolerated. Okay, so under this particular situation, two things can happen. At a particular point, the system, the output is increasing with time. Now, after a while, it might so happen that the system will become a non-linear one. A non-linear one. Just try to remember a spring, right? So if you go on stretching the spring, initially the displacement will be, or the system will act like a linear one, isn't it? But after a while, if you go on stretching the string, after a while the string may break down, or the entire system will become non-linear. So the output will not go on increasing towards infinity, but if the output becomes very large, then either the system will not remain linear, the system will become a non-linear one, or the system may break down. Now, so far is this clear?
Yes, ma'am.
Now we'll learn two notions of stability. One is Peebo stability, and the second one is asymptotic stability. So, what is the full form of Peebo? This is an acronym. Peebo stands for bounded input, bounded output. So, the Peebo stability actually refers to, is associated with a forced system. A forced system means a system on which you have applied an input signal. A forcing function is there on the system, right? So, such a system is called a forced system. That means there is an input, and Peebo stability, the notion of Peebo stability states that if the input to the system, for a linear system, if the input to the system is bounded, then for a stable linear system, the output has to be bounded, right? So when the system is excited by a bounded input, the output is unbounded. So this notion of stability is known as Peebo stability, bounded input, bounded output. And the second notion is associated with a free system. That means there is no input, and the system is exhibiting its dynamic behavior because of its initial conditions. Is that clear? Hello, is it clear?
Yes, ma'am.
So a free system means the system is exhibiting dynamics because of its initial condition, and there is no input signal, right? So asymptotic stability, this particular notion states that In the absence of any input, a stable system should always be able to regain its zero motion state. That means will always be able to regain its initial condition of motion. Initial condition of motion. So in the absence of any input, the output tends towards zero. That is the equilibrium state of the system irrespective of initial conditions. So this stability concept is known as asymptotic stability. Let's get back to that particular figure, that particular example. So already we know that this is a stable system. Suppose there is no disturbing force. We have not applied any disturbing force. Only we have changed the initial position of the ball. Can you follow the cursor?
Yes, ma'am.
So instead of placing the ball at this particular point, we have discussed this point is basically the equilibrium point, because if you don't disturb the ball while resting at this particular point, the ball will remain at this particular point forever. Now, if we don't apply any disturbing force, instead we change the initial condition. That means instead of placing the ball at this position, suppose we place the ball over here. Then what will happen? Since the initial condition has been changed. So the system will now execute some dynamic motion, and ultimately it will regain this, or it will come to the position of rest, isn't it? Is it clear?
Yes, ma'am.
And instead of placing the ball over here, I can place the ball over here or over here. That means I can go on changing the initial conditions, but whatever be the initial conditions, the in this particular case, the ball will always regain this particular position, or will be able to regain its equilibrium position. So this kind of behavior is described by the notion of asymptotic stability. So the advantage of linear system is that if a linear system is pivot stable, then the linear system will be asymptotically stable and vice versa. That means if the system is asymptotically stable, then the system will also be pivot stable. That is the advantage of linear system. But that is not true for non-linear systems. Now, why we are interested about pivot stability? Bounded input. If the input is bounded, the output should be bounded. Why? Because if we excite the system with an unbounded input, if the input itself is unbounded, then it's expected, or intuitively we can say that yes, the output of the system will be unbounded, because we know that a stable system will always try to follow the input. So if the input itself is unbounded, then obviously the output will be unbounded, right? So nothing can be concluded about the stability of the system. Have you understood?
Yes, ma'am.
So that's why to judge the stability of a system, we'll have to excite the system by a bounded input. And if in that case the output comes out to be a bounded one, then obviously the system will be a bounded input, bounded output, or Bibo stable. Now, here we are claiming that for a linear system, the ultimate response to a bounded disturbing force is independent of the nature of the disturbing force. So, what is our claim? That is, we can generalize this or we can say that the output response of a system doesn't depend upon the nature of the input. Whatever be the input signal, if it's bounded, then a linear system, if it's bounded, a linear stable system will exhibit bounded output, or will exhibit a motion which is bounded in nature. And why we are claiming that the output response of the system is not dependent upon the input signal, because if we consider the disturbing force, then we are applying the disturbing force, and after a while we are actually completely removing the disturbing force from the system, isn't it? And only after removing the disturbing force from the system, we are observing the response of the system, and depending on the nature of the response, we are classifying a system to be a stable one, or an unstable one, or a limitedly stable one, isn't it?
Ma'am, would you please repeat this part?
So far, what we did, we excited a system with a bounded disturbing force. We perturbed, not actually excited, we perturbed a system with a bounded disturbing force, right? And after a while, we remove the disturbing force from the system. Do you agree? Can you recall?
Yes, ma'am.
So we are removing the disturbing force, and only after the removal of the disturbing force, or only after withdrawing the disturbing force from the system, we are actually observing the output response of the system. Is it true?
Yes, ma'am.
So we are actually observing the output response of the system after removal of the disturbing force. And depending on the nature of the output response, if it's bounded, we are classifying the system to be a stable one. If it's not bounded, if the output response is not bounded, then we are classifying the system to be an unbounded one, so on and so forth. Isn't it?
Yes, ma'am.
So that's why we can intuitively we can argue, for the time being we can intuitively argue that the output response of the system is not dependent on the nature of the input. Only one constraint is imposed on the disturbing force, that is, the disturbing force has to be a bounded one. Do you get the logic?
Okay, ma'am.
Is it absolutely clear, or do I have to repeat?
No, ma'am, it's clear.
Okay, so that's why we are arguing like this, that the output response of a system is not dependent on the nature of the input force. Though there is one exception that we'll discuss later on. So that's why, for our convenience, we are assuming that the input to a system is unit impulse. So if we consider a disturbing force, then the nature of the disturbing force that we are assuming is a unit impulse. Okay? So I guess you know what is a transfer function, open loop transfer function, closed loop transfer function, etc.
Yes, ma'am.
So we can write down this expression: CDS is the transformed version of the output response because of the disturbing force that we have applied, and after a while we have removed it from the system, and we are observing this response after removal of the disturbing force. So CDS by RS. What is RS? RS is the reference input or the input signal. Okay. So in this case, we have, or rather, this ratio CDS by RS is defined as TS, where TS is the closed loop transfer function of the system. I guess you do this.
Yes, ma'am.
So CDS by RS is the closed loop transfer function. Please note, closed loop transfer function. It's written over here. TS is the closed loop transfer function of the system, right? So CDS is TS into RS. Now, since we have assumed RS to be unit impulse, hence rather RT is unit impulse. Hence, RS will the value of RS will be equal to 1. Do you agree? Yes or no? Please respond.
Yes, ma'am.
Okay. So actually what we want to observe, that is CDT. You remember CDT as time t increases, limit t tends to infinity, right? So that means the time response of the system, or we are interested about finding out CDT, isn't it? This CDT. So for that, what we'll have to do, we'll have to take the Laplace inverse of Ts only. So we can see that CDS is equal to Ts into Rs, where Rs is equal to 1. Hence CDT, we are interested about this physical quantity, and CDT is nothing but Laplace inverse of Ts. So if we consider a general nth order system, let us consider an nth order system. So what is meant by uh, nth order system? Can you tell me? What is meant by nth order system?
Sir, yeah, ma'am, in denominator of the transfer function, the maximum power of S is n.
Maximum power of what?
Ma'am,
Maximum power of what?
S.
Yes. Continue.
ma'am,
Yes.
ma'am. Here we're trying to find out the output of the system because of the disturbing force only, right?
Yes.
Okay.
And will ultimately generalize this to any impulse force. Okay.
Okay. Okay.
Uh, so output power of maximum power of Ace. Can you be a little bit more precise?
Ma'am, the system should have n number of poles.
That is also not a precise definition. Okay, I'll come to that. Partially correct. So nth order system means this transfer function Ts can be expressed as a ratio of two polynomials which are functions of S. S is the complex frequency. That means Ts is equal to, we can write, you have pen and paper with you?
Yes, ma'am.
So write down Ts can be expressed as Ps by Qs. Am I correct?
Yes, ma'am.
So Ps is the numerator polynomial. Ps is the numerator polynomial which is function of S, and QS is the denominator polynomial which is also a function of S. So only if you define, first you will have to define QS, that is the denominator polynomial. Then only you can say that the order of the polynomial or maximum power of S, isn't it? Then the definition will be complete. Do you get my point?
Yes, ma'am.
On the second one, the system will have yes, QS. So I'll come to that. The system will have a number of poles, not n number of poles. Poles could be open loop poles or poles could be closed loop poles. Similarly, zeros could be open loop zeros, zeros could be closed loop zeros as well, right? And open loop poles are not same as the closed loop poles. So whenever you will be talking about poles and zeros of a system, you should always mention whether the poles are closed loop poles or open loop poles, or whether the zeros are open loop zeros or closed loop zeros. Am I clear?
Yes, ma'am.
So in this case, so while you say that, while you define like this, that the number of poles, actually it should be the number of closed loop poles. So an nth order system, a general nth order system will have n number of closed loop poles, and what is QS? What is the name of this polynomial QS? Is there any name?
Characteristic
Characteristics of
equation.
equation.
আমি
Characteristic
এখনো
polynomial actually.
yes, characteristic polynomial আমি এখনো ইকুয়েট করিনি জিরোতে, so I will not get an equation, right? So QS is a polynomial which is the characteristic polynomial of the system. And if we equate QS to 0, that means QS equal to 0, then we'll get an equation which is known as characteristic equation of the system. Not the characteristic equation, the characteristic equation of the system. Right? So QS equal to 0, that is the characteristic equation. If we solve the characteristic equation, this particular equation, which is QS equal to 0, we'll get, since it's an nth order equation, so we'll get n number of roots of the equation, roots of the characteristic equation. Yes or no?
Yes, ma'am.
So n number of roots of the characteristic equation, and hence from this discussion it's clear that the roots of the characteristic equation are identical to the closed loop poles of the system. So we can use these two terms, that means closed loop poles of a system or roots of the characteristic equation of the system, synonymously or interchangeably. ঠিক আছে?
Okay, ma'am.
So please to recall, closed loop poles of a system are same as the roots of the characteristic equation. Now let's assume that the system has m number of closed loop zeros, right? Then the transfer function, closed loop transfer function, not an open loop transfer function. Closed loop transfer function, that is Cs by Rs, where Cs is the output of the system and Rs is the reference input, right? Ts can be expressed as a ratio of two polynomials, Ps by Qs, and then expanded, if we expand these two polynomials, then the polynomial, since Ps, the order of Ps is equal to m and the order of Qs is equal to n, hence these two polynomials can be written as b0 is to the power m plus b1 is to the power m minus 1 plus bm minus 1 is plus b whole divided by a0 is to the power n plus a1 is to the power n minus 1 plus a n minus 1 is plus a n. Should I zoom it?
Ma'am, it's fine actually.
Okay, it's legible.
Yeah, ma'am.
Yes, ma'am.
So I'll follow this particular convention throughout this course. Now you can write it in a different way as well. In some books, you will find that the polynomial is being described as bm s to the power m, bm minus 1 s to the power m minus 1, right? So likewise, b1s plus b0. You get my point?
Yes, ma'am.
An mth order polynomial can be written in that particular way also, but I'm convenient in this particular convention, so throughout this course I'll follow this particular convention. So for Ps, these are the coefficients of the polynomial b0, b1, bm minus 1, bm, and for Qs, the nth order polynomial in the denominator, the coefficients of the polynomial are a0, a1, an minus 1, a. These are the coefficients. Okay. So we know that Qs is the characteristic polynomial, and if we equate that to 0, we'll get the characteristic equation of the system. And if we solve the characteristic equation of the system, then we'll get the roots of the characteristic equation. That means by solving the characteristic equation, we can find out the locations of the closed loop poles of the system on the S-plane. Should I repeat? Is it clear?
Yes, ma'am.
So if the transfer function of the closed loop transfer function of the system is given, right, that means the numerator polynomial as well as the denominator polynomial are known to us, which implies that the coefficients of the numerator polynomial and the denominator polynomial are known to us, then with the help of partial fraction we can find out the not only the locations of the roots of the characteristic equation, right, as well as we can find out the response Cs by Rs, that is Ts, Cs by Rs. So if Rs is known to us, then we can find out Cs, and from Cs, now I have dropped the suffix d. So from Cs again we can find out Ct. So if we can obtain Ct, then from that expression we can find out what is going to be the magnitude of Ct as t tends to infinity. Have you understood? So
Yes, ma'am.
in a nutshell, this is fixed that we have excited the system with the help of a bounded input, right? Now, to judge the stability of the system, we'll have to observe CT. That means the output response of the system vis-a-vis time, right? So if we can find out the expression for CT, then looking at that particular expression, we can find out what is going to be the magnitude of CT, output response of the system, as T increases. So if we find that CT dies down to zero, then we can say the system is going to be stable. And if we find that as time t increases, CT goes on increasing farther and farther, and as time t tends to infinity, CT theoretically becomes infinite, then we can say that the system is unstable. So that is the task that we want to perform. Understood?
Yes, ma'am.
So what is going to be the output response or output time response? That is very clear from this example. Suppose Cs by Rs, the closed loop transfer function is uh, specified as or given as a some constant a by s minus sigma. S minus sigma. So from our knowledge on system uh, theory, we know that in this case there is a first order system and there is one single closed loop pole, and the pole is located on the s plane at s equal to sigma, right? So far, is this clear?
Yes, ma'am.
So now if rs is unit impulse, that means rs is equal to 1, right? So cs will be equal to a by s minus sigma, and from that, by taking Laplace inverse, we can find out ct. You see, ct is equal to a e to the power sigma t, isn't it?
Yes, ma'am.
So what is the conclusion? The conclusion is, if we know the locations of the roots of the characteristic equation on the s plane, then we can find out the mathematical expression of the output response of the system in this manner. ঠিক আছে? So now we'll consider the different uh, the locations of closed loop poles, different locations of closed loop poles on the S plane, all possible kind of locations of the closed loop poles on the S plane, or in other words, the locations of the roots of the characteristic equation on the S plane, and we'll try to find out the response term contributed, that will be contributed by a closed loop pole on S plane. So let me make it clear. So suppose for an nth order system, we know that n number of closed loop poles will be there. So we can locate n number of closed loop poles, assuming that the transfer function is given, transfer function is known. So we can find out n number of roots of the characteristic equation, and we can place all those roots on the S plane,
Ma'am,
right? Yes.
just one question. Can you scroll up just a little bit more? Yes, ma'am, there. Ma'am, in that equation, CS by RS you equals to A by S minus sigma. You then you found CT equals to A e to the power sigma T. Ma'am, you considered here the reference input to be an impulse function, right?
Yes.
Okay, thank you.
The reason is we have assumed that the output response of the system doesn't depend upon the nature of the input. That's why, for our convenience, again I'm repeating, we have taken RS to be a unit impulse. Is it clear? So now, so for an nth order system, n number of roots will be there, right? So first root, second root, third root, so on and so forth. So if we can locate, or if we can find out the first root of the characteristic equation of the system, then what is going to be the output response of the system because of that particular first root, that we can find out, right? Similarly, what is going to be the output response of the system because there is a second root of the characteristic equation, that we can find out. Am I clear? পার্শিয়াল ফ্র্যাকশন যখন নিই তাই তো করি।
Ma'am, can you please repeat this?
Okay, suppose a third order system. So how many closed loop poles will be there? Three closed loop
Three.
poles.
Yes.
Three closed loop poles. Okay. Now, if we can solve the characteristic equation, then we can find out the closed loop poles of the system, the
Yes.
locations of the closed loop poles of the system on the S plane.
Yes.
So closed loop pole number 1, closed loop pole number 2, closed loop pole number 3, right? So
Yes.
this these three closed loop poles will contribute their own response, right?
Yes, ma'am.
And the
Yes.
combined response, since we are considering a linear system, hence the combined response of the system will be summation of all summation of individual contribution by the three roots.
Yes, ma'am.
Clear? So now
Yes.
this concept can be extended for a number roots as well. So now let's try to look at this particular table and we'll try to find out that if the if a closed loop pole or root of the characteristic equation is located at a certain point on the S plane, then what is going to be the response term contributed by that particular root? Clear? So types of root, the first column, the heading of the first column is types of root, and the heading of the second column is nature of the response term contributed by the root. So is it clear?
Yes, ma'am.
Now the first case, single root at S is equal to sigma. That means we are talking about a real root. S equal to sigma. I'm assuming that you know all these things: real root, complex conjugate, root pair, all these things, right? You know all these things. Yes or no? Yes or no?
Yes, ma'am.
So single root at is equal to sigma. This is a real root, and already we have seen that the response term that will be contributed by this root of the characteristic equation is a e to the power sigma t. Now, the second case, again we know that the roots of the characteristic equation can be simple or can occur with multiplicity. So what is meant by multiplicity? That means if the if a particular root has a multiplicity of the order 2, that means at the same location on the S plane, two roots will be occurring. That means we'll get repeated roots at a particular location on the S plane. I guess you know what is meant by multiplicity. Repeated roots. Please respond.
Yes, ma'am.
So next we are considering roots of multiplicity k. That means k number of real roots. Real roots are occurring at this particular location, which is s equal to sigma. So at this particular location s equal to sigma on the s plane, we are getting k number of repeated roots. So in that particular case, the response term, if we do partial fraction and if we go for a Laplace inversion, then we'll find that Ct will be equal to a1 plus a2t plus a3t square plus dot 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 ak, since the order of multiplicity is k. So it will be ak t to the power k minus 1 whole multiplied by e to the power sigma t. So please do it in the class. Now let's assume that the closed loop transfer function of the system is a by s minus sigma square. S minus sigma whole to the power 2, and rs is unit impulse. Find out Ct. Do it and do it fast. We'll say,
Ma'am, my mic is not working properly. Can you please repeat what we have to do?
suppose the transfer function, closed loop transfer function is given a by s minus sigma whole square. That means two
Okay.
roots are there at s equal to sigma, right?
Okay.
Find out
Okay.
Ct where rs is unit impulse. Actual
Ma'am,
control
minus 80 e to the power sigma t.
minus 80. Minus can a by s minus sigma whole square. কারুর
Ma'am,
হয়নি?
ma'am, the answer is e to the power sigma t
Eh,
times a times t by gamma 2. মানে t.
By Gamma 2, what's gamma 2?
That means, ma'am, A times T times e to the power sigma T.
A times
T times e to the power sigma 2. E to the power sigma T.
Yes, ma'am. At e to the power sigma t. At e to the power sigma t.
would be AT to the power sigma T.
Yes, ma'am.
Sure.
Yes, ma'am. That's what is coming. Yeah.
Please check. Please do check.
A1 plus A2T, A to the power sigma t.
A1 plus A2T whole multiplied by e to the power sigma T. That should be the answer.
Yes, ma'am. Yes.
So please brush up your knowledge on Laplace transform and inverse Laplace transform. So then we can generalize that particular expression for k number of repeated roots, and the CT. In this case, the response term will have an expression which is A1 plus A2t plus A3t square plus AK t to the power k minus 1 whole multiplied by e to the power sigma t. So I'm showing the expressions of CT. It's your responsibility to find out. It's your responsibility to find out whether these expressions are correct or not. So next we consider complex conjugate root pair at s equal to sigma plus minus j omega. So if the root is a complex one, then there has to be the conjugate pair. So complex conjugate root pair at s equal to sigma plus minus j omega. So because of this omega term, because of this frequency component, will get at the output, will get a sinusoidal function which is given by sine omega t plus beta, right? And if the denominator at the at the numerator, if there is a constant a, then it should be multiplied by a. And because of this real part sigma, non-zero real part will get a term which is e to the power sigma t. So the contribution term will be, or the response term can be expressed as a into sine omega t plus beta whole multiplied by e to the power sigma t. Next, please take Laplace inverse and try to find out the response term. That means try to find out the expression for CT for this particular case. That is your assignment. And in my class, pen and paper as well as calculator, these things are must. From next class onwards, you must have a calculator with you. Now the next case is complex conjugate. This case only at this particular location we are assuming that we are having repeated roots and the number of repeated roots is equal to k. That means complex conjugate root pairs with multiplicity k at s equal to sigma plus minus j omega, right? So because of this sigma part, e to the power sigma t, this component will be there, but only this part will get modified because now we are getting multiple roots at that particular location. So the CT, the expression for CT will be A1 sine omega t plus beta 1 plus A2t sine omega t plus beta 2 plus dot ak tk minus 1 sine omega t plus beta k, and whole multiplied by e to the power sigma t. So for this case, write down, your assignment is to write down the transfer function, closed loop transfer function, and therefrom your assignment is to find out the response term CT. And for the fourth case, just consider that the value of k is equal to 2. So at that particular location, you have two complex conjugate root pairs, and the order of multiplicity k is equal to 2. Again, please write down the transfer function and try to find out the unit impulse response CT. Is it clear what we'll have to do?
Yes, ma'am.
Okay. Now, so we have considered real roots with multiplicity. We have considered complex conjugate root pair, and we have also considered complex conjugate root pair with multiplicity greater than 1. Now, one thing is clear, you see. Suppose if we consider a system having a root at s equal to sigma and having another two roots at s equal to sigma plus minus j omega. So one real root on the s plane, as well as two complex conjugate root pairs, right? So what will be the what will be the response of the system? So the first component of the response will be because of this root, let's call it C1, and the second component of the response will be because of this complex conjugate root pair, and let's call it C2T. So the actual response of the system, that is CT, will be equal to C1T plus C2T. Do you agree?
Ma'am, can you repeat this whole thing again? The last part.
Suppose we do have a system for which we have a real root at s equal to sigma and two complex conjugate root pair at s equal to sigma plus minus j omega. So far, is this clear?
Yes, ma'am.
So now, if we want to observe the output response of the system, then we can say that the output response CT will have two components. The first component will be because of the presence of this real root, and the second component of the response will be because of the presence of these two complex conjugate root pair. Do you agree?
Yes, ma'am.
And since the system is a linear one, already I have explained this. Since the system is a linear one, hence the actual response of the system because of these three roots will be CT, which is equal to C1T plus C2T.
Yes, ma'am.
Okay, try to remember this. So now we are considering conjugate root pair on imaginary axis, on j omega axis. On the j omega axis, so complex conjugate root pair at s equal to plus minus j omega. Am I audible?
Yes, ma'am.
So s equal to plus minus j omega. So complex conjugate root pairs are occurring on the imaginary axis. Since sigma is equal to 0, hence from this expression we can derive the output response, the nature of the output response. Since sigma is equal to 0, so e to the power sigma t will be equal to 1. Or directly we can write down, by taking Laplace inverse, we can say that the output response Ct in this case will be a sine omega t plus beta. That means the output will get undamped oscillation with constant amplitude A and constant frequency or angular frequency omega. Isn't it?
Yes, ma'am.
Now, the next case is complex conjugate root pairs with multiplicity k at is equal to plus minus g omega. Okay. So we'll get multiple complex conjugate root pair on the imaginary axis. Since we are having multiple roots at the same location and complex conjugate roots on the imaginary axis, the output response Ct will have an expression which is a1 sine omega t beta 1 plus a2 t sine omega t plus beta 2 plus ak t to the power k minus 1 sine omega t plus beta k. Okay, so for this case also take uh, a value of k to be equal to 2, right? Again write down the transfer function, closed loop transfer function, and find out Ct for unit impulse input. And the last two cases, we're left with these two cases. We have considered real roots with multiplicity. We have considered complex conjugate root pair as well as complex conjugate root pairs with multiplicity. We have considered roots on the imaginary axis uh, as well as roots on the imaginary axis with multiplicity. So this location is only this look. We are left with this particular location. That means single root at origin of the S plane. So if a single root at the origin of the S plane occurs, then the output response will be constant. Let's call it A. So Ct will be constant with time A, right? And the last case is multiple roots at origin of the S plane. So roots with multiplicity k at origin. And the response term will be given by a1 plus a2t plus ak tk minus 1. Again, you form the transfer function. Here it will be very simple, that is a by s square. A by s square, and try to find out, it's your assignment. Please not try to do find out Ct.
Ma'am, here I have a question.
Yes.
Uh, so, ma'am, in determining these response terms in time domain, uh, are we not considering how many zeros are there in the transfer function, or no zero is present on?
Have you forgotten partial fraction?
Ma'am, I couldn't understand what you have told.
Partial fraction কি করে করো সেটা ভুলে গেছো?
না ম্যাম,
What are
মানে
the
আমি
role, what or rather what is the role of the numerator polynomial?
নো ম্যাম, অ্যাকচুয়ালি মানে আমি বলছি যে যেমন এখানে লাস্টেরটায় মানে 8 নাম্বার কেস যেটা, মানে রুটস উইথ মাল্টিপ্লিসিটি কে অ্যাট দ্য অরিজিন, মানে যদি কোনো জিরো না থাকে, জাস্ট যদি ট্রান্সফার ফাংশনটা এরকম হয় যে এ বাই এস টু দি পাওয়ার কে, তাহলেও তো মানে অরিজিনে কে মাল্টিপ্লিসিটি একটা রুট থাকে, তাহলে এর যদি আমরা ইনভার্স নেই তাহলে তো এটা জাস্ট হয়ে যায় এ বাই ফ্যাক্টোরিয়াল কে ইন্টু টি টু দি পাওয়ার কে মাইনাস 1। মানে হচ্ছে একটা সাম কনস্ট্যান্ট ইনটু টি টু দি পাওয়ার কে মাইনাস 1। তাহলে আগের যে টার্ম গুলো থাকছে ওগুলো অ্যাকচুয়ালি থাকে না, কিন্তু যদি কোনো জিরো থাকে মানে সেই অনুসারে তখন পার্শিয়াল ফ্র্যাকশনটা করা যায় আর কি, তখন মানে এই ধরনের টার্ম আসতে পারে। তাই বলছি মানে এখানে জিরো কতগুলো আছে বা না আছে সেগুলো তো মানে ধরা হচ্ছে না। জিরো মানে অ্যাকচুয়ালি কনস্ট্যান্ট গুলোর মধ্যে কোনোটা
না না
জিরো
না
হতেও
না,
নাও হতে পারে, এরকম তো ব্যাপারটা।
zero will contribute towards the magnitude associated, but associated with each root, right? But if
হ্যাঁ
you only solve the denominator polynomial, if you solve the denominator polynomial in its domain, then you will get the locations of the roots of the characteristic equation, and actually the locations of the roots of the characteristic equation or your denominator polynomial or your characteristic equation will decide upon the nature of CT.
Ma'am, the last case is actually the engineered version of the second case with just sigma equal to 0.
Yes.
Yes.
So, ma'am, if there is no zero, then a1 to a k minus 1, all these constants will be 0, and only there will be one constant. So that is the case. So
Uh,
we have generalized the
the,
formula here.
exactly. Exactly. This is the most generalized version of CT that we have written down.
Okay.
As you can see, see, we have taken different phase angles. So this is the most generic form of expression of CT. Now is it clear?
Yes.
So do you have any other question?
No, ma'am. Okay.
So far, is this clear to everyone?
Yes, ma'am.
কার কার অ্যাটেন্ডেন্স দিতে হবে রোল নাম্বার